Training role, Shakadutula, I'm the PMR of Scholar Identifies, and today's session on the topic design of steel structure. So, as we in this week, you might have studied about the different type of lacing system and Batten patterns. So, uh, these are the different connections we are using for the our compression member building. So we are actually studying about the compression member, different columns and all, and these are the two type of systems which we are using for our compression member to hold two different elements. So first is the lacing system. So, what exactly are the racing system? You might have already seen these kind of structures in your daily life when where you are literally connecting two different elements of a compression members. So mostly the racing system are flat bars, or it can be in the angle section, channel section, or tubular section. So if you see this figure, in this figure, you can see some angle section are used as the lacing bars. Whereas in this the below picture, you can see some flat plates are used as the lacing bars, lacing columns. Okay, so we have two type of lacings. One is single lacing and second is double lacing. Mm. So if the connection is made using a single plate, if two elements are joined using a single plate, then we are calling it as a single lacing system. And if we are using it as in a crisscross position, or we are using two laces, then we are calling it as a double lacing system. Okay. So after this, what are the different failure modes in our compression member? Either a complete built-up member, a complete section including laces and the column members, either they completely buckle up, that is if some load is applied from the both ends, so buckling can happen at the complete compression member. Or secondly, there are chances that the main component of our compression member fails. Because of that, if there is a failure in main section, this lacing will come off. Okay. Other thing is there is a distortion in section, like mainly due to axial loads. There can be a distortion in section which can cause a failure into our lace members. And lastly, actually our lace member fails. It can be due to overloading or some other reason, or poor connection. Our lace member can fail. Okay. When we come to the lace members, we have different requirements. So if you see your ISO 800, ISO 800 clause 7.6 will give you all the general requirements and the design parameters for our lacing system. So in this case, first point is that compression member should have a radius of gyration about the axis perpendicular to the plane of lacing, not less than the radius of gyration about the axis of plane of lacing. This is what it mean is, and second point is if a single lace system on opposite side of the compartment should be roughly in the same direction. So uh, if you see this figure, so in this system, you can see that there are two lacing system. One is applied at this side, and one is at the opposite side. So their direction should always be similar. It should not like it should be uniform and in the same direction. Third point is that in both kind of lacing system, either double or single lacing system, it shall not be combined with the cross members perpendicular to the longitudinal axis of the strut, unless all forces resulting from the deformation of the strut member are calculated and provided for the lacing and fastening. So, what it means that normally when we are providing a lacing system, on the opposite side, like if this is the first phase and behind this, like if we see this number, we are providing lacing here and we are providing lacing here. So all it should not be combined with the cross member. We should not combine this lacing with the cross member unless this thing is satisfied, like unless force resulting from the deformation of straight members are calculated and they are provided properly. So we should not provide extra cross links between two lacing which are at the opposite end of our compression member. Okay, so these are the various design specification which are already given in our IS code. So first is the width of lacing bar. So if we are providing rivet or bolt connection, minimum width should be more than 3 times the nominal diameter of the end connector. Okay, this is simple thing. Next is the thickness of the lacing bar. So minimum thickness should be, it depend on our length between inner bolts or welds. So if it is a single lacing system, then thickness is given by L by 40. And if it is a double lacing system, thickness is given by L by 60. Okay. Next is the angle of inclination. So this is our lacing system. So this angle of inclination, so the third point, thickness of lacing bar means this thickness lacing bar. So it should be inclined not less than 40 degree and not more than 70 degree. So the angle should be in between 40 and 70 degree. Next is the spacing of lacing bar. What should be the spacing between two lacing bar? So maximum spacing, it depends on the slenderness ratio. So if this is the formula which is given for the spacing of lacing bar, and where R minimum is the spacing and lambda is your slenderness ratio. Okay. So next is the force in the lacing bar. So this is a IS 800 clause. It's directly written the same thing. The lacing of compression member shall be proportional to resistor total transverse shear force at any point. So if our system is have axial forces, so mainly we will design it based on our total shear force, and it should be equal to at least 2.5% of the axial force in the member. Okay. Next is the total transverse shear force. Like the same thing is given in the formula base. So the transverse shear force is given by 2.5% of the axial force. Okay. So if we have a single lacing system, in single lacing system, we are telling force on each bar is given by shear force divided by number of transfer system into sine theta. Theta is our angle of lacing. And when it comes to the double lacing system, this n will be number of transfer system will become 4 instead of 2. Okay. Next is the slenderness ratio. So we have studied about the slenderness ratio. It is given by effective length divided by radius of gyration. So it should not be more than 145. The slenderness ratio should not be more than 145, and if it will depend on the type of welding. So if we have a single lacing welding, then our L is given by L. Like we have studied for the compression member. Like our effective length will depend on the type of our system. Same way, if we see in this lacing system, our effective length will depend on the type of laces, type of welding of our lacing. If it is bolted at end in single lacing, if it is bolted with double lacing, then L effective is given by 0.7 L. And if we have a welding connection, then it is again given by 0.7. Okay. And if in case of flat bars, our thickness is given by T and width is B, then we can calculate our slenderness ratio as R will be given by R is our radius of gyration. It will be given under root moment of inertia divided by area. So in case of our flat bars, moment of inertia will be Bt cube by 12 and area will be B into T, right? This is a simple formula, I guess everyone will know. So solving this thing, we will get LE under root 12 divided by T. B will go T, Q square will go square will be cut by under root. So we will get this formula. So if in case of flat bars, what we have to check? We have to check that our LE into under root 12 divided by T should be less than 145 degree. Yeah, new guys, Haripan, Haripan. Okay. If anybody have any doubt, you can ask me now. Then otherwise, we'll go to the design step of our racing system. So if we come to the design of our lacing system, first step would be the to find the effective length from the actual length. It depends on our end condition and the type of welding as we have seen in the previous slide. So next is the we will assume the value of lambda between 30 to 60 for build section, and then we will for the given value of lambda we can find the design compressive strength FCD. It is given in table 9 of IS 800. Next step is to calculate the area. So area will be given by force upon compressive strength, design compressive strength, right? Strength is equal to load upon area. So area is equal to load upon strength. So PD will be given to us in a question most of the time. Next is the based on our area, we will choose our build-up section, which type of build-up section we want. Like we will get based on our area, and we will arrange our members in such a way that IZZ will become closer to IYY. So moment of inertia in Z direction should be almost equal to the moment of inertia in Y direction. So based on that, we will choose our member, and from this we can calculate our R minimum, and then we can calculate our slenderness ratio. And from the calculated lambda, again we will go to our this table 9C, and we can get the exactly design compressive strength from it. And from this compressive strength, we can calculate our design load. And if our design load is greater than the given load, then we can say that our section is okay. If it is not coming greater than our given load, then we will repeat our steps. Not, not 5 to 7, actually 2 to 4. Next is based on this thing, we will provide the lacing system. So next will be the how to design a lacing system. So for designing a lacing system, first we have designed our compression member for the lacing system. Second is that we have to design the lacing system. So for lacing system, first we will choose what kind of lacing system we are providing in our either single lacing or double lacing, and based on that we will determine the length and spacing of the lacing bar. So this is the spacing of lacing bar. We will calculate it based on the type of lacing we are providing. Okay. Then we have to calculate the gauge distance. So what is the gauge distances? It is the distance between the edge of our member and this lacing wherever this intersection is happening at that point. So this is the intersection point. From this point, like the intersection of two laces, from this point to the edge, that is our gauge distance. So we will calculate this gauge distance and then we will calculate the spacing. The spacing we will calculate. It is give so this x is equal to 2g plus s, and where s is our clear spacing. So these are the different formulas we are using for the single lacing system, double lacing system, and in case of both single and double lacing system. So after calculating the spacing, we will calculate the slenderness ratio. So it will be uh, find the slenderness ratio and check for the. So we will calculate the slenderness ratio L upon R minimum, and R minimum we are calculating from here. L effective we will calculate, then R minimum either it will be given, we'll see in the some example, and from this we will calculate the slenderness ratio and check that it should be less than 50, and it should be less than actually 145. Okay, then we'll find the length of each lacing between inner and bolt and find the effective length. And this is what we have seen in the table. If it is a single lacing system bolted, then it is given by L effective is equal to L. If it is a double lacing system, L effective is equal to 0.7 L. And for welding, it is 0.7. Same, all the formulas we have seen before. Then we will calculate the thickness based on our type of lacing system we have calculated, and then we will calculate our slenderness ratio based on our this formula. Okay. So these are the different design steps for designing a lacing system. Last is the similar. We will calculate the compressive strength. Then we will calculate the transverse shear force, which is 2.5 percentage of our axial force. And then we will calculate the, this is the same if we are providing bolted connection, then we will do the bolt design. So we'll select the bolt diameter, find the width, and then number of bolts required. And then if we check if the number of bolts are sufficient to withstand the load of member. So this was the basic design pattern for the lacing system. Next are the batten plates. So if we are connecting our two members using some angles, then we are calling it as a lacing system. But if we are connecting our two members using a singular plate in this form, then that is called as batten plates. So they main function is to connect the components of the built-up columns in two parallel plates, and it is generally used where we have only axial loads, and normally we are providing flats or plates. We can provide channel section or tubular section also, but normally we prefer flats or plates for it. So these are the what is exactly is the batten plate. So these are the general requirement for our batten plates. So this is already given in IS 800. You can read from there. First thing is the first thing is compression member composed of two main components should have individual member of the same cross section, and they should be symmetrical around the major axis, and the radius of gyration about the axis perpendicular to the plane should not be less than the radius of gyration about the uh, along the parallel to the plane. Okay, that's the same design step we have seen in the our lacing system, that our radius of gyration perpendicular should be equal to or more than the radius of gyration in that plane of the batten. Next is the batten compression member. Uh, or subjected to a say, applied moment or later force in the plane of batten shall be designed according to the exact theory of elastic stability or empirically based on the verification of test. So these are just the requirements. I don't think you will require it for the design term. Next is the batten shall be placed opposite to each other at each end of the member and at points where the member is stayed in its slam as far as practical should be spaced proportionally and uniformly, and it should be such that it should like number of battens should be divided in such a way that there should be minimum of 3 bays. So all the battens should be uniformly distributed, and it should be in such a way that we have minimum of 3 bays. Okay. Next is the slenderness ratio. So slenderness ratio of batten is taken as 1.1 time. The the effective slenderness ratio is taken as 1.1 time the given slenderness ratio, the maximum slenderness ratio. Okay. This is how we will design our batten system. So first step is calculating the transfer shear, same as we were calculating for our lacing system. It should be 2.5 percentage of our actual load, and then we will calculate the longitudinal shear along the column itself, which is given by VC divided by NS. Next is we are calculating the moment. Again, we will calculate the effective slenderness ratio, and we will select our shape of batten based on our design, and we will calculate the gauge distance and then calculate the distance between the bolt centers. Next is we will calculate the spacing. So I think all of these design steps are actually similar to what we are doing for the lacing system. We are calculating the effective, we are calculating the slenderness ratio, then gauge distance and designing everything. Then we will calculate the spacing between two plates. And this is the formula that are for spacing, that C divided by I minimum should be less than 50 or 0.7 of the slenderness ratio. And minimum 3 number of batten we are providing, as we have seen in the requirements, that we should have 3 minimum of 3 bays. Next is we will find the size of the end batten. So these are the different formula to calculate the size of end battens. You can see in the slide also, it's similar to that thing. Next is we will calculate the size of intermediate battens. So our end battens and intermediate battens have a different design steps. So you can see all these design steps in the PPT itself. And last is we will design the connection for our better system. Okay. So this is all what you might have studied in this week. So we will go to the different problems for the this week, which will help you in solving the assignment 8. So the first question is, if a laced column is subjected to axial compression, the design of a lacing bar in the laced column is done to resist the force arising from transverse shear, the shear force and bending moment arising from transverse shear, the axial force and twisting moment arising from transverse shear, the twisting moment and shear force arising from transverse shear. What do you think is the answer? It's a simple question. So, in the first slide only, we are seeing that normally we are telling that we will have axial forces. In case of axial forces also, our lacing system will be designed for the transverse shear, right? So, what will be the answer? First one. So, in case if there is only axial compression, the design is done based on a design is done to resist transverse shear. We have seen that formula now, 2.5% of axial forces, right? So second question is, the thickness of a lacing bar for a single lacing should not be less than 1/30th of the effective length of lacing bar, 1/40th of the effective length of lacing bar, 1/50th or 1/60th. E. So it is given in clause 7.6.3 in case of our single lacing system. The thickness should not be less than 1/40th of the effective length. So you are correct. Answer is B. In case of double lacing system, it is taken as 1/60th. Next question is, a built-up double laced column is 9 meter long and one end of the column is fixed and the other end is free. The effective length of the laced column will be is given in IS 800 in appendix. We have given that in case of different type of ends, how we can calculate the effective length. So first thing is, okay, yeah. Actually, you're correct that based on the end condition, effective length will be given by 2 into L. L effective is equal to 2L, that is 18 meter. But in case of our laced column, when we have lacing along with the, in case of normal column, 18 meter is correct. But when we have laced column, the effective length of laced column is given by it will be 1.05 of 18. So that is given in this IS 800 only. Like in case of Batten, we are telling it should be 1.1, I think. 1.1 of L effective. In case of our laced column, effective length of laced column is given by 1.05 of 18. Okay. So the answer will be C, 18.9 meter. Is it okay or you have doubt? Okay. Uh, so then, so the next question is, in a laced collar, 18 diameter bolts are used for the connection. In that case, the minimum width of the lacing flat should be. So the clause you can use to calculate it. So in case of our bolts or rivets, what we are telling, the minimum width of lacing bar is 3 times the nominal diameter. So in our case, nominal diameter is 18 mm. If we calculate it, it will be 54 mm. Okay. Alhamdulillah. So thickness of batten plates shall be more than 1/50th of the distance between the innermost connecting lines of the rivets or bolts perpendicular to main member, should be less than 1/50th of the distance between the innermost connecting lines of the rivets or perpendicular to the main member. It should be more than 1/60 of the distance between innermost connecting rivet was perpendicular to main member, or it should be less than 1/60th of the distance between innermost connecting the rivet was perpendicular. So in clause 7.7.2.3, it is given at the last that the thickness of plates attached should not be less than 1/50th of the distance between innermost connecting line perpendicular to the main member. So it should be more than 1/50th of the. Okay, this is the simple question. Next question is, a lacing member of length 400 mm is attached to the column using weld. Find the effective length of the lacing member. So we know we have seen all the formulas. In case of welding connection, effective length is given by 0.7 of total length. So in our case, total length is 400 mm. So effective length will be 280 mm. Okay. Next question. A laced column and a batten column, each of them is subjected to factored axial compressive load of uh, P. What should be the total transfer shear in lacing system and batten system respectively? It should be 2.5% for lacing system and batten system, 2.5% for lacing system, but 5% for batten system, 5% for lacing system, but 2.5% for batten system, or 5% for both lacing and batten system. So if we see different clauses, this is 7.6 for lacing system. It is given as that transfer shear should be at least 2.5% of axial force. Okay. And in case of batten, it is given as the transfer forces should be equal to 2.5% of total axial force. So based on these two clauses, we can see that our option A is correct answer. Okay. To the next question. A laced column is designed for the factored axial compression of magnitude 1100 kilonewton. The lacing bars are provided as single lacing system in the column and are arranged in two parallel plates. If the length of each of the lacing bar is 320 mm, and each lacing is inclined to 45 degree from the vertical axis of the main component. Find the magnitude of the design axial force in each lacing bar. So what is given to us? That compressive force is applied at 1100 kilonewton. The angle is given as 45 degree, and length of each lacing bar is 320 mm. Yeah, that's all. And what we have to calculate? We have to calculate the axial force. How we will calculate it? Take 5 minutes if you can calculate it. Tell the 19.45 kilometers. Let's see. So for us, we have given the compressive load P as 110 kilonewton. From there, we can calculate the transverse shear force. That will be 2.5% of our compressive load, axial force or compressive load. So it is coming as 27.5 kilonewton. Next is the what is given to us. It is arranged with it is flat lacing bar arranged in two parallel planes. So if it is arranged in two parallel planes, what we are doing, we are dividing this transverse shear force in by divided by 2, so that we can get the uh, shear stress per plane. In each plane, what is our shear stress? Then we can calculate our axial force. Axial force will be given by our shear stress divided by sine 45. So uh, if this is our one force, if we have to calculate our axial force, this is sine or cos 45. If this is our normal stress and this is our shear stress, we have to calculate our normal stress. It will be, sorry, this is our axial force. So it will be divided, sorry, transverse shear stress will be axial stress into sine theta, right? If this is our if this is our axial force will be in direction of our lacing only, and this is our shear force. Then shear force is given by P sine theta. So P will be V upon sine theta. So sine 45 theta is 45. We can calculate and we will get as 19.45 kilometers. So you are correct. Our axial force will be 19.45 kilometers. Next question is that if the effective length of a flat lacing bar is 400 mm, what shall be the minimum thickness of the lacing bar provided in double lacing system? So for us, what is given is effective length is already given. Next, they are telling that what should be the minimum thickness of lacing are provided in double lacing system. So in double lacing system, thickness will be given by L effective divided by 60. So from LE by 60, we can get 6.7 mm. And secondly, uh, maximum permissible value of slenderness ratio is 145 in our case. So L is given to us. From here, we are calculating our R, radius of gyration. It is covered by 2.76. And using the second formula, uh, maximum thickness is given by r into under root, radius of gyration in case of flat lacing bar is given by thickness divided by under root 12. So thickness will be r into under root 12. That will give us thickness as 9.56. So we have two thickness, 6.7 mm and 9.56. So what is asked to us? It is asked minimum thickness. So it will be given as maximum of these two values, which is almost nearby to the 10 mm. Okay. So we are seeing two factors. First is if we are taking double lacing system, in that case, how thickness is given to us is LE by 60. But if we uses the different formula, if we are going through the radius of the, slenderness ratio formula, from there, if we calculate our thickness, we are getting 9.56. So normally what we are taking maximum of these two values, which will give us the minimum thickness of our lacing bar, and it is coming as 9.56, which is approximately equal to the 10 mm. Okay. So next question is, two ISMC 300 are placed back to back with a spacing of 185 mm and a single lacing system with an inclination of lacing bar of 45 degree. If the gauge length is given as 50 mm and the grade of steel is Fe 410, the design compressive strength of the lacing bar will be. So, what is given to us? Length of the lacing thread is given to us. Sorry. First, we will calculate the length of our complete lacing thread. So, we have a single lacing system and we have spacing of 185 mm. This is a single lacing system. And we have to calculate the length lacing flat. Then it will be given by spacing plus gauge length. This spacing plus one of this gauge length, then one of this gauge length, 185 plus 50 plus 50 into cosecant of 45 degrees. So at this 45 degree we have given. So this length into cosecant 45 degree will give us the length of our complete lacing flat, which is coming as 403.05 mm. Next is we will calculate the thickness of our lacing flat. Well, since it is given as single lacing system, our thickness is given by L divided by 40. So it will be 10.08 mm. Okay. Next is we will calculate the radius of gyration. Same formula, thickness divided by under root 12. So radius of gyration is coming as 2.91. From here we will calculate the slenderness ratio L upon R. It is given by L is 403 and our R is 2.91. It is 138. So this is less than 145. 145. That means our design is correct. So from IS 800 table 9C, we can see for FY 250 and L upon R 138.5, and we can calculate the compressive strength, which is given by this is the we are using the interpolation method. So for one value it is 66.2, other value 74.3. So 74.3 minus this is the interpolation formula which we are using into 8.5. Okay, which will give us the compressive strength as 67.41. So it is answer will be in between 67 to 68 megapascal. Okay. So this is the last question. If slenderness ratio considered for the design of column is 100, the maximum effective slenderness ratio considered for the design of the same collar raised with Batten system will be. So clause 7.7.1.4 for the Batten system tell that in case of Batten system, we are taking effective slenderness ratio as 1.10 of the given slenderness ratio. So calculating this, our slenderness ratio will be 110. And if we go for the case of our leasing system, it is given by 1.05. Okay. So these are the questions which will help me for the assignment for this week. If you have any doubts, you can ask me now. I will upload the record PPT now only. Recorded lectures I have to upload for previous 2-3 sessions. I will upload them today. If there are no doubts, then we can close the class for today. Thank you, sir. Thank you, sir. Thank you, sir.